In this video, we will describe the Lorentz transformations. Lorentz transformations are the relation between position and time coordinates of the same event as seen in different reference frames, according to the special relativity. We have seen in a previous video that the Galilean relativity relates two reference systems, one of them moving at constant speed. We defined a relationship for events happening in these reference systems. We also saw that Galilean relativity breaks down when high speeds are involved. More important, Galilean relativity doesn't follow the second Einstein postulate. In this sense, Henrik Lorentz developed a set of equations that can be used on special relativity to substitute the Galilean transformation. In such a case, we use the same scheme as for Galilean relativity. This means we assume that there are two reference systems, S and S'. S' is moving at constant speed v, that can be a fraction of the speed of light. Each reference system has its own timer. T for the frame S, and T' for S'. Now, let's suppose that there is a light source in S'. At some instant, we generate a flash of light, and observe how a point at the spherical wavefront evolves in each reference system. Note how, if we consider a spatial three-dimensional case, the points P and P' are fourth-dimensional vectors. This is, 3 spatial coordinates and 1 temporal coordinate. This is one of the most important features of the Einstein's relativity. It is clear that for S, the wavefront has the form, and a similar form for S'. We can easily confirm that these equations can be written as both equations are equal to 0, then we have. Finally, it can be proven that the relationship between coordinates can be written as follows. We need to note that, in order to simplify the process, we have supposed that the changes happened only in the x direction. This means that the coordinates, y and z in a three-dimensional case, are not affected by the transformation. We can find similar relationships between the times in the different reference systems, as follows. These 4 equations are considered the Lorentz transformations. Let's solve an example to see how the previously obtained equations work. Example 4. A reference system S' has a velocity v equals 0.56 c relative to the system S. The clocks of S and S' mark 0 seconds when the origins coincide. An event is observed in both systems. The event takes place at x equals 800 meters, and at time t equals 3.0 microseconds, as measured by an observer in S. What is the time t' of the event, measured by an observer in S'? Could you solve it? Answer. We know that the relationship between times is the following. Then, we have to calculate first the relativistic factor gamma using its definition. By substituting the values, we get gamma equal to 1.2. Now, we can insert this value on the time equation, as well as the values of the speed, distance and time as follows. Then, we finally get, as expected, we found that there is a change in the time due to the relativistic effects. In the same way we have developed the relationships for the positions and times, we can get relationships for the speeds. We now suppose that there is a spaceship traveling at speed u with respect to s prime. We can see that using differentiation, we get, if we make the quotient between the differential of position and differential of time, we see that, in this case, as the speeds on the y and z directions are changing, we have to calculate also the speeds in these directions. Finally, we get the speeds as follows. These equations are the speeds observed from S, and can be confusing, due to the different speeds on them. Then, let's solve an example to clarify this issue. Example 5. If a spaceship approaches Earth at 0.5 c, and shoots a canister at a speed of 0.75 c. At what velocity does an Earth-bound observer see the canister, if it is shot directly toward Earth? Could you solve it? Answer. We know that the speed of the spaceship is 0.5 c, and the canister moving with respect to the spaceship has a speed of 0.75 c. The Lorentz transformations for the speed in the x direction is the following. Then, substituting the values on this equation, we get. Then, finally, the speed of the canister, observed from the Earth, is 0.9 c. Note how the result doesn't exceed the speed of light, as stated by the Einstein's postulates. This result contradicts the value calculated by Galilean relativity. Then, we confirmed again that Galilean relativity doesn't work for relativistic speeds. It is important to note that the factor gamma sometimes is called the Lorentz factor instead of relativistic factor. Finally, we should notice that we have covered the relativistic effect on the speeds by using the Lorentz transformation. In next videos, we will explore the effects of relativity on the momentum and energy, and their consequences. Stay tuned.